Let's look at what happens to a carbonyl when we add an amine. So far, we've looked at adding water or an alcohol to a carbonyl. What happens when we add a nitrogen-based nucleophile? We are going to form what we call an imine. So in this reaction, we have a carbonyl. Here we've got acetone as our starting material. We've got methylamine, a trace amount of acid. And then what will happen is that we will end up losing the oxygen of our carbonyl, and it will be replaced with the nitrogen of the amine. We're going to be losing water, and we consider this a condensation reaction. This is essentially loss of water or a small molecule. And when they would run these reactions, they started calling them condensation reactions because they'd start to see water on the sides of the glass as they were heating this. And so they'd see this condensation in the glass, which is why they would call it a condensation reaction. The oxygen in our water is coming from the oxygen of our carbonyl. Let's walk through the mechanism here. We see that we're in a trace amount of acid. And there are other ways to draw this mechanism where you don't protonate our carbonyl, but I'm going to show you this way. It's reminiscent of all the other acid catalyzed reactions that we've done before with carbonyls. So in the presence of our acid, our carbonyl will be protonated. Just like we've seen before. Then we're going to be adding our amine. Attacking the carbon of the carbonyl, which we know is partially positive, and then we're going to push our electrons up. Again, I like to draw what didn't change. We have our OH here, and then we now have a new nitrogen carbon bond. We have our methylamine, and it still has 2 protons on it, right? It still has these 2 hydrogens, which are now extremely acidic. Our conjugate base that's present can deprotonate this. And what we have here is what we call a hemiaminal. This hemiaminal is not very stable. It's actually more thermodynamically favored to have a carbon-oxygen double bond. And we know the steps of this mechanism are actually reversible. What happens with this hemiaminal is that it reacts further to form our imine, which has a double bond to the nitrogen. And a carbon-nitrogen double bond, as we'll see, is actually more thermodynamically favored. What will happen next is, as you look at this, you know that we need to form this carbon-nitrogen double bond, and as it stands, we still have this OH group. We need to make this a good leaving group. Now, we can't simply have this leave as an OH minus. That only happens under strongly basic conditions where we can have a hydroxide leave. So we can't do that. However, we do have a small amount of acid present, so we could protonate this and make it water. We have a lone pair on a nitrogen that could then kick it out. So let's do that. I'm going to flip this compound over so it looks more like the product that we have. So here I've got the nitrogen with the methyl group on the top. It still has that hydrogen. And here we still have our 2 methyl groups that are from the starting acetone. We can now take our conjugate base and we will deprotonate this nitrogen to form our desired imine. Again, these reactions are reversible. You can imagine that if we start with our imine, we could push this back to the carbonyl. We would simply need to add a lot of water. We would just need to do this in a solvent of water and heat it, and it will form the carbonyl. This is reminiscent. These reactions are thermodynamically driven. Okay. These reactions are thermodynamically driven though. And if we start with the carbonyl, these reactions are thermodynamically driven, and this carbon-nitrogen double bond is thermodynamically favored. But again, we could push the equilibrium of this reaction if we were to add a lot of water. Imine formation also has the same aspects of this reversibility as we've seen with other carbonyl reactions. And we've talked about microscopic reversibility, where if we start with this imine product, we can get back to the carbonyl. And it goes through the same intermediates. So let's go ahead and do that. If we form this imine, which I have redrawn here, we could imagine that if we do it in a solvent of water, we could push it back to the carbonyl. So let's do just that. Let's redraw our imine, and we're going to go through the backwards reaction to form our carbonyl. Now, the first step of this is going to be the last step of our forward reaction. And the last step here, it was deprotonation. So we need to do the opposite here. We're going to use HA, and we're going to simply protonate our imine. And the next step, we had lost water. So what we're going to do now is we're going to add water back in. We have that very acidic hydrogen here on our water. So we're going to deprotonate it. And check it out, we just made our hemiaminal. Now notice here I have this simply flipped from what I had before. But the oxygen was on top and the nitrogen was on bottom. But here is our hemiaminal. Remember that we can't isolate this. And again, we are in the presence of a lot of water. So although each step of this reaction can go back and forth, and that's exactly what happens in these reactions, if we have tons of water, we can push it back to the carbonyl. We need to lose this amine, but we know that we can't lose it as an N-. It cannot be negatively charged. So what we're going to do is protonate our amine. Which will make it a great leaving group. Notice here, when we have acidic conditions, our leaving groups are always neutral after they leave. We typically protonate them. Now, under basic conditions, we can have an anion leave. Under acidic conditions, you should only be having neutral compounds leaving. I'm going to push the lone pair on this oxygen down, and then we're going to kick out this amine. We have our protonated carbonyl, and we can simply deprotonate this using that conjugate base from our starting acid. And then here we have our carbonyl back. So a couple things I want to mention here in these reactions with imines. They are only acid catalyzed. Whereas before we saw addition of water to form hydrates could be done under acidic or basic conditions, these amine reactions to form imines can only be done under acidic conditions. And the second thing here is that we have to be very careful that we're only adding a trace amount of acid. These are typically done at a pH of 4 to 5. And the reason why is because our amine could get protonated very easily if we have too much acid. This has a pKa of around 35, whereas this protonated amine has a pKa of around 10. Very easy to protonate these. If you have too much acid present, you'll protonate all of your amine. And this is a bad nucleophile. So in order for our amine to be nucleophilic, we need it to be neutral. If it's protonated, it's not going to have that lone pair that could go attack. And the second thing with these imine formations is that there is some stereochemistry involved here. What happens if we don't have a symmetrical ketone? Here we've got two methyls, and so the nitrogen has this methyl on this side, but that would be the same product as if we had it on the other side. Let's look at an example where we're going to see this imine have two products, and they are not going to give us a 1-to-1 ratio, and let's talk about that. Here I've got benzaldehyde and aniline, trace acid, and you know that we're going to replace the oxygen of our carbonyl, and we're going to make an imine. You could imagine that the two phenyl rings could be on opposite sides or on the same side. Here we've got an E and a Z conformation of this imine. And we know from our previous organic chemistry studies that E alkenes are more thermodynamically favored. They are lower in energy. Because these reactions are thermodynamically controlled, remember we've got reversible steps. The product with the lowest energy is going to be favored. Remember, this reaction is reversible. So if you were to form this Z conformation where the phenols are on the same side, even though we know this is slightly higher in energy, we know that this could go back in the mechanism, and then it could form the more stable product, which is exactly what happens as we do these reactions. So this E conformation is thermodynamically favored. There's another thing I want you to notice on this slide. Here we're starting with an aldehyde. Our previous example was with a ketone. Notice that for carbonyl chemistry, a lot of times you'll learn one reaction and then you can apply it to a lot of different molecules. I want you to see the similarities between all of these mechanisms that we're learning. It feels like a lot of reactions we're learning, but really, it's a few of the same steps. The steps for this imine formation were very similar to when we formed our hydrates. The same concepts we're using for the mechanisms. Rhodopsin is a light-sensitive receptor protein involved in visual phototransduction. The visual pigment retinol reacts with the lysine chain of opsin to give rhodopsin. Notice the aldehyde in the teal circle of retinol reacting with the amine of lysine to form an imine in the pink circle. The reversibility of imine formation allows for the removal of retinol so it can be recycled and reused. Pretty cool, you have imines in your eyes. Let's do another example. What happens if we have a secondary amine? Our previous example just had one alkyl group on our amine. In this case, I have two alkyl groups on our amine. I'm still using acetone and a trace amount of acid, but we get a different product here. We don't get an imine. Let's think about what that imine would look like, right? We would have this CH3, a double bond to our carbon, but this nitrogen would be positive. In this case, this isn't what we isolate. And so we don't form an imine here when we have two alkyl groups on our nitrogen. What we form is called an enamine. And here's what it looks like. You'll notice that our nitrogen added where the carbon of the carbonyl is, right? And then here we have this alkene that formed. This is why we call them enamines. This en is from an alkene. And so here we've got this alkene and then a nitrogen bound where that carbonyl is. In these reactions, we also still lose water. The oxygen from our carbonyl is here in the water, And our hydrogens here for our water come from our amine, and they also come from this carbonyl starting material. I know this looks kind of weird. Let's walk through the mechanism, and I think you'll see that it's really similar. There's only one difference with an enamine formation than an imine formation. Again, we don't want to make that nitrogen with a positive charge, so something at the end has to happen to make that alkene, which gives us a more stable product. These reactions are also reversible. Starting with our ketone, in the presence of acid, we're going to do what we've done before with reversible reactions of carbonyls in acid. We're going to protonate our carbonyl. This is going to make it more electrophilic. We're going to now add our secondary amine. We're going to attack the carbon of the carbonyl. We have a nitrogen with 2 methyl groups and a hydrogen. It is now positively charged because we use those electrons to form the new carbon-nitrogen bond. That hydrogen on that amine is very acidic, so we can use our conjugate base of our starting acid and we will deprotonate there. And check this out. What did we just make? We made something that an intermediate that we made. In our imine case, we just made a hemiaminal. We know that these are not stable and we wouldn't isolate this. So we need to keep going to make this more stable enamine product. The next step of the reaction is going to involve trying to make this OH group leave. Remember, we're under acidic conditions. OH minus cannot leave. I can't stress this enough. I see it all the time, that if you're under acidic conditions, OH minus does not like to leave, but water can leave. So let's turn this into water. We're going to use one of the lone pairs on our oxygen to protonate our hemiaminal. We're going to use the lone pair on our nitrogen to push down and kick out that water. Here, I'm just going to flip this molecule over so the nitrogen is on the top. I had it on the bottom, but we made a new carbon-nitrogen double bond with that first arrow. You'll notice here, this looks like our imine. This is looking pretty good, but this really isn't that stable. We could even draw a resonance structure here to show that the carbon of this carbon-nitrogen double bond is not very happy. I've got a positive charge here. And so what really happens is this is starting to look like an E1 elimination. And the electrons push down to make a double bond. And this is exactly what happens with our enamine formation. I'm going to draw it from our major resonance contributor, which is the nitrogen having the positive charge. And this bottom resonance contributor, notice that that carbon doesn't have a full octet. So let's do it from the top one here. Here's our hydrogen. I'm going to have A minus. This is the conjugate base of our starting acid. Because this hydrogen is a lot more acidic than it normally would be. Now we're going to push the electrons down, form a double bond here. Something on this carbon has to leave, and it's happy to. The nitrogen is positively charged, so it wants electrons. Again, deprotonate, push down to make a double bond, and then the pi bond between the carbon-nitrogen bond, those electrons move up to the nitrogen. That forms our enamine. Pretty cool. The concept of microscopic reversibility also applies for enamine synthesis. I think it would be a great exercise for you to look at enamine formation and try to start with your enamine. You'll pretend like you did the reaction in a lot of water, and I want you to redraw the mechanism to form your carbonyl. You'll notice that for the first step, and I'll give you a little hint, this first step here, to go from the product back to the carbonyl, would require a protonation step. So you might start here, push electrons down, take the double bond, and protonate. Pretty cool. This kind of enamine chemistry, this kind of mechanism drawing is going to happen again and again in carbonyl chemistry, and we'll learn this in chapters to come. It's a nice intro to learning about this. And so I encourage you to practice drawing these mechanisms. Draw them with me and then rewatch the video and draw it again. It will help you a lot as you start to understand these. And that's it for carbonyl reactions with amines. We made imines which are carbon, nitrogen, and that's it with carbonyl reactions with amines. Here we did acid catalyzed imine and enamine formation. Again, both have to be done under acidic conditions. And be careful when you make your imine to make sure it's the thermodynamically favored imine, because these are thermodynamically controlled reactions. And that's it for our carbonyl reactions with amines. We learned about imines and we learned about enamines. Both of these reactions require acidic conditions, just slightly acidic because you don't want to protonate your nucleophile the whole way. These reactions are thermodynamically controlled, and so the most thermodynamically favored product will form. I highly suggest you dive in and start to practice these mechanisms. The mechanisms we've learned so far for reversible carbonyl reactions under acidic conditions are very, very similar. Make sure you practice this, and so you become very efficient at running through these reactions and understanding the forward and the backward mechanism. And I'll see you in the next video.